Hello and welcome back. This is going to cover section 7.2. So it's a continuation of our definition of the inverse trigonometric functions. So last time we looked at the sine, cosine, and tangent. We'll look at the remaining inverse trig functions and then some problems involving those. So this will be our definition of the secant, cosecant, and cotangent, their inverse functions. We won't produce the full graphs of these, but I want to focus on their restricted range, which was a big part of our last discussion on the inverse sine, cosine, and tangent. So let's just remember those because we can relate them to these other ones. So we had the inverse sine, the inverse cosine, and the inverse tangent. The inverse sine function was restricted between negative pi over 2 and pi over 2. So the right side of the unit circle. The cosine was on the top half of the unit circle, so in between 0 and pi. We can produce a little diagram like this. So between 0 and pi. And then the tangent looked like our restricted inverse sine, except it was undefined at negative pi over 2 and pi over 2. Remember, we had some horizontal asymptotes there. So let's consider the inverse cosecant, secant, and cotangent. So the cosecant, that is the reciprocal of the sine function. So they share some similar properties, and they're restricted. The restricted range of the inverse cosecant will look similar to the restricted range of the inverse sine. So it's the right side of the unit circle from negative pi over 2 to positive pi over 2. So it'll still be defined on the extremes there, except for at 0. Because since the secant is 1 over sine, wherever the sine is equal to 0, the cosecant was undefined. So we have to skip over that point at the angle of 0. There's a similar issue with the inverse secant. The range is similar to the inverse cosine, except for where the cosine is equal to 0, and that's at pi over 2. So we'll have to skip over that point. So we're between 0 and pi, but not equal to pi over 2. And the inverse cotangent will also look similar to the inverse cosine, except it's undefined at 0 and pi. That's where we had vertical asymptotes for the cosine graph. We can have pi over 2 up here. So These little diagrams are useful when we're trying to answer questions involving the inverse trig functions. We can reference these in order to determine what angle we should produce. We need to be within these restricted ranges. So just to review again, if we have the inverse sine, cosine, and tangent down, the cosecant is similar to the inverse sine, just not defined at 0. The inverse secant is similar to the inverse cosine, so the top half of the unit circle, except where the cosine is equal to 0 at pi over 2. And similarly to how the inverse tangent looks like the inverse sine, the inverse cotangent looks like the inverse cosine, except not defined at those endpoints. So let's practice using these, and this table from the textbook defines it in a similar way. They say the inverse secant between 0 and pi, the inverse cosecant between negative pi over 2 and pi over 2, and the inverse cotangent also between 0 and pi. So let's practice using these in a few examples. And define the value of some inverse secant, cosecant, or cotangent functions. Let's look at the first one. We have the inverse secant of positive 1. So I'm going to say this is equal to some angle. We can take the secant of both sides, so we're saying 1 is equal to the secant of some angle. Where is that true? Well, the secant is 1 over cosine, so we can always relate it back to sine and cosine. That's saying that the cosine of some angle is equal to positive 1. And the inverse secant is restricted between 0 and pi. And it can't be pi over 2, so we have a little hole there. So on the top half of the unit circle, the cosine is equal to positive 1 at an angle of 0. And the secant will also be equal to 1 there. So I can say the inverse secant of positive 1 equals 0. That's the angle from 0 to pi where the secant equals positive 1. All right, part B gives us the inverse cosecant of 2. So let's do a similar maneuver here. This is equal to some angle. We can take the cosecant of both sides. So 2 equals the cosecant of some angle. Well, that will happen where the sine is equal to 1/2, because they are reciprocals of each other. So I'll think about the restricted range of the inverse cosecant, which was from negative pi over 2 to positive pi over 2, not including 0. And the sine is equal to 1/2 in the first quadrant at pi over 6. So we're calling that coordinate point. So I can say the inverse cosecant of positive 2 should be pi over 6. Part C, we have the cotangent, the inverse cotangent of negative root 3. So set this equal to some angle, take the cotangent of both sides, so negative root 3 equals the cotangent of something. And the cotangent, that's the cosine over sine. So that means that the cosine should most likely be negative root 3 over 2, and the sine should be 1/2. I'm looking for that coordinate point. And we said earlier the inverse cotangent had the restricted range from 0 to pi, not including endpoints. So I'm looking for that coordinate point -√3/2, +1/2. That sounds like 5 pi over 6 over in the second quadrant. So I can say the inverse cotangent of -√3 equals 5 pi over 6. So I'm still relating them to things that I know on the unit circle, coordinate points involving the sine and cosine. So we can still do that. Or if you have secant, cosecant, or cotangent values memorized, then even better. All right, let's look at some more composite functions. So involving these inverse trig functions. So now in the last video, we had like the same function, like the sine of the inverse sine of something. And we had to be very tricky about what's the domain and range. Here we have different functions plugged into each other. So let's develop an approach here. We have, in this first example, the sine of the inverse tangent of 1/2. We want to try to evaluate this. So what should we do? So I'm going to propose an approach involving building a triangle, because we can take what's inside. This inverse function is equal to some angle. The output of an inverse function is some angle. We could also argue like the input of the sine, this is going to be some angle. We can call that theta. So I'm going to do that. I'll say inverse tangent of 1/2 should equal some angle. I'm going to call it theta now. Well, let's take the tangent of both sides. I can say 1/2 equals the tangent of theta. Well, from here, I can build a triangle. And the output of the inverse tangent is between -pi/2 and pi/2, and it's positive, so we should be in the first quadrant somewhere. So our triangle should look like this. So I'll call this theta, and tangent is opposite over adjacent, so I'll make that 1 and this 2. So why are we doing this? Well, if we use this triangle, because ultimately, since we said the inverse tangent of 1/2 is equal to theta, we're ultimately going to be asking, what is the sine of theta? And we can use this triangle, since we're calling this theta, to answer the question. Sine is opposite over hypotenuse, so let's find out what this missing hypotenuse is via the Pythagorean theorem. We can say 2 squared plus 1 squared equals c squared. So 4 plus 1, 5 is equal to c squared, so square root of 5 will equal c. That will be our hypotenuse here. So I can use this triangle to answer the sine of theta is equal to opposite over hypotenuse. And then let's rationalize. That will be square root of 5 over 5, multiplying the top and bottom by the square root of 5. So let's re-express this in terms of the original statement. We were asked for the sine of the inverse tangent of 1/2. We can say that's equal to the square root of 5 over 5. So we have to do this whenever we don't have a nice like unit circle value in here. So just to summarize, if you have an inverse trig function inside of another function, well, that inverse trig function is equal to some angle. So I just set it equal to theta. Then we took the tangent of both sides in order to undo this inverse trig function. So 1/2 equals the tangent of theta. You get a statement like this, that you can build a triangle, solve for some unknown sides, and then use the triangle to answer the outside trig function. Let's see a couple more examples. It takes a little bit of practice to get used to. So this one is asking for the cosine of the inverse sine of -1/3. It's probably still good to check, is this -1/3 in the domain of the inverse sine? Inverse sine was between -1 and +1, so that should work out. It won't give us an undefined value. All right, so let's go through a similar approach. This inverse sine inside is equal to some angle. I'll just call it theta. And then let's take the sine of both sides. Let's undo the inverse trig function. So -1/3 equals the sine of theta. Now let's build a triangle. And let's see. I'm going to say the sine is negative and the inverse sine is bound between -π/2 and π/2. So we should be somewhere there in the fourth quadrant. So our triangle should look something like this. So we'll build a triangle. I'm going to call this theta. Sine is opposite over hypotenuse, so I'll call this side length -1. Hypotenuse should be 3. And then let's solve for that missing side length. So let's call this x. We'll say x squared plus -1 squared should equal 3 squared. So x squared plus 1 equals 9. That means x squared equals 8. Let's take the square root of both sides. This should be positive because we're in the third quadrant. X is positive. So I'll take the positive square root of 8, and then that will reduce to 2 root 2. Because 8 is 4 times 2. You can write it out here. Square root of 4 is 2. That comes out as a 2 on the outside, and we have that 2 left inside. So that will be our side length here. Let's relabel it. So we have our triangle. We said what was inside was equal to theta, so we can re-express this as just asking for the cosine of theta. Theta is here in this triangle. Cosine is adjacent over hypotenuse, so the adjacent side length is 2 root 2 over the hypotenuse of 3. So let's just re-express this in terms of the original problem. The cosine of the inverse sine of -1/3 will equal 2 root 2 over 3. So we are again taking the inverse trig function that's inside, set it equal to some angle, undo the inverse trig function. This time we took the sine of both sides. Use that statement to build a triangle. Solve for your missing side length, and then evaluate that outer trig function using your triangle in some right angle trigonometry. So it's a pretty useful trick. All right, let's look at one more. Now we're given the tangent of the inverse cosine of negative 1/3. So let's follow that same process. I'm going to take inverse cosine of negative 1/3, set that equal to some angle. Well, let's stick with theta. We can call this y or whatever we want to, but we'll use theta. And let's remember that the inverse cosine is bound between 0 and pi. We'll take the cosine of both sides, so negative 1/3 equals the cosine of theta. So theta must be, if the cosine is negative, somewhere in the second quadrant. So we will get some triangle like this. This will be theta. We're saying the cosine is negative 1/3. Cosine is adjacent over hypotenuse. So negative 1 will be that lower side length, 3 is the hypotenuse. And then let's solve for our missing side length. We actually get a similar triangle from our last one. Yeah, we have a side length of negative 1 and a hypotenuse of 3. So from that, just to steal our work from that last question, this side length should be 2√2. We could get it again via the Pythagorean theorem if we needed to. And then let's use this triangle to evaluate the outer trig function. Find the tangent of theta. Tangent is opposite over adjacent. So 2√2 over negative 1, or negative 2√2. So let's answer in terms of our original question. We are given the tangent of the inverse cosine of negative 1/3. That will be equal to negative 2√2. So I use this triangle method whenever we have an inverse trig function inside of another function. So we take the inverse trig function, set it equal to an angle, undo the inverse trig function, build a triangle, and then use the triangle to solve the outer trig function. Okay, the last section, they're calling this writing a trigonometric expression as an algebraic expression. So let's see what they mean. They want us to write the sine of the inverse tangent of some unknown angle u. I want to write this as an algebraic expression, meaning we want to write it being equal to something that doesn't involve a trig function. Let's apply that same approach from our previous section. So let's take the trig function inside. We don't have an angle this time, or we don't have an input value. We just have some unknown, a variable, or some unknown constant. But let's just go take that same approach. I'm going to call this some angle theta. Then we can take the tangent of both sides. So u, whatever u is, will be equal to the tangent of theta. At this point, we can build a triangle. I'll call this theta. Tangent is opposite over adjacent, so we can see this as a u over 1. Opposite side length is u, adjacent side length is 1. And let's solve for this hypotenuse. 1 squared plus u squared will equal c squared. So we'll just have to take the square root of both sides. 1 squared is just 1. So we have 1 plus u squared equals c. That will be our hypotenuse. Now let's use this triangle to evaluate the outer trig function, which is the sine. So we can say the sine of theta is opposite over hypotenuse, u over the square root of 1 plus u squared. And with values, usually we rationalize the denominator, but let's just keep it like this for now. So we can say the sine of the inverse tangent of u equals u over the square root of 1 plus u squared. So it seems kind of weird, but this actually becomes a very useful maneuver later on in calculus. Sometimes you'll want to re-express things without trig functions as an algebraic expression. That can make some things easier to work with. So this followed the same procedure as our last subsection. We have an inverse trig function inside of a other function. So take the one that's inside, set it equal to an angle, undo the inverse trig function. This time we took the tangent of both sides. We use this statement to build a triangle, and then use the triangle to answer the outer trig function. So if you see this kind of request, write something as an algebraic expression, that's what they're talking about. This result here is an algebraic expression. It's no longer trigonometric. Okay, that's it for this section. So we defined the properties of the inverse secant, cosecant, and cotangent functions. We found the value of the inverse secant, cosecant, and cotangent functions for some applied problems. And then we had those last two pretty interesting sections with composite functions where we built a reference triangle and solved from there. All right, that's it for this section, and I'll see you next time.